My name is Jeremy Fairbank, and today we're going to talk about asynchronous patterns in JavaScript. We're going to briefly review some of the historical ways that we've been doing async in JavaScript up to this point, and then look at how we can use a couple newer patterns to help solve some asynchronous code, such as with async await functions and with observables. So very briefly about me. I work for a company called CG, and I'm a web developer, and I work remotely, primarily on front-end development, and we do also full stack and some mobile development as well. So in JavaScript, we have a lot of asynchronous patterns, and probably the most well-known would be the callback. And I like to think of the callback as sort of a token, where we provide a token to some asynchronous API, and then that API can sort of cache in that token, so to speak. So it's doing something in the background, and whenever that data is available to us, it can notify us by using the token we provided to it. So concretely, it kind of looks like something like this, something we're all kind of familiar with. We have a fetch user by ID. We provide the ID and some sort of callback, and then we can retrieve the user inside that callback and make forward progress in our code. However, we know some issues can arise with this callback pattern. We can have this sort of incurring debt with these callbacks, where once one piece of it is asynchronous, all of it needs to become asynchronous. So we end up with lots and lots of callbacks. So we may end up with some code like this, where I need to fetch a customer's name based on their order. So I'll first fetch the order, and once I have that, I can fetch the customer. But notice what's happening here. We have to keep nesting in callback after callback, which makes this harder to read and maintain for the future. So this has been aptly called callback hell, because it's really hard to maintain this, and to go back and refactor this would be a nightmare. Another potential problem here is we're using the node style callbacks here that take an error first and then the payload second and the callback. And this is sort of an atypical, non-standard way to handle errors, but it's just how we do it with these callbacks. These errors won't be thrown. We have to do our due diligence, basically, to check if there was an error first and then handle it. So it'd be nice if we had some asynchronous patterns that would let us do this in a more fluid manner that could maybe even integrate with like try-catch blocks or something like that. So moving along from callbacks, we introduced sort of the opposite, where we reverse this relationship, where instead of providing a token to the API, let's let the API provide a token back to us. And this is what we all know and love, or maybe hate, as the promise. So instead of providing a callback to the asynchronous API, it will provide back to us a promise that will eventually fulfill with the value that we're looking for. So when I fetch my customer name, I first fetch the order, and then I can attach these then callbacks. I can pull the order out, and then from there I can fetch the customer. And so what I get out of this is I can flatten out all those deeply nested structures I saw with the callbacks and make this a little more readable and cleaner to deal with. But even though this helps out some, we can run into some similar issues even with promises. Instead of having deeply nested callbacks, we can have long chains of then callbacks. Because again, as one piece becomes asynchronous, the rest of our code needs to become asynchronous. Another issue with promises is that they swallow errors. So you may have seen this before, you may not, but if there is an error thrown in our code, we may not know about it, or if there's a promise rejection, it's going to be swallowed, and we may not know that until later on when there's a bug in our UI or we're in some sort of inconsistent state. So this is a problem with promises. Now to overcome that, we can attach and catch callback, but we have to sort of do our due diligence, so to speak, to handle this. If we don't remember to handle it, then these errors could occur and we don't know about it. But thankfully, some browsers like Chrome will at least notify us with a warning these days to let us know we didn't handle a rejected promise. So that's kind of the history of where we've been so far, and we've been kind of getting there. Promises and callbacks are still very useful patterns, and I'm not here to knock on them today by any means, but they do have their limitations, as we've seen. So we have sort of a checklist of ways we would like to handle asynchronous code in a better manner. So we'd like for it to be more readable and maintainable, obviously. It'd be nice if in certain situations we could write synchronous looking code, but it would still be asynchronous non-blocking, so it's not going to affect the browser or the user experience. It'd be nice if we could also introduce and utilize native flow control constructs with our code as well. And then finally, it'd be nice if maybe we had a more declarative and versatile API over what we get with promises. And so today we're going to learn how we can accomplish some of these goals through some newer asynchronous patterns like async await and observables. So let's dive in and start looking at async await. So this is a new feature of JavaScript. It is now part of the standard as part of the ES 2017 spec. And it's actually available now in the newest version of Chrome and Edge, and I can't say for certain on Firefox or Safari, but it's eventually going to land. So this is definitely standard JavaScript, and we can even transpile it down to older browsers. But what these async functions are is we get this async keyword that we prepend to a function, and then we can declare it as an asynchronous function. And then inside we get to use these await operators, which as they suggest, they're going to await some operation. In this case, they're going to await a promise, and they can pull out the fulfilled value of that promise. So now we can write synchronous looking code that underneath the hood is using promises for us. These async functions, we can also return values from them, and we'll look at that more in depth later because it may not be exactly what you think it is when we return something from one of these. And we can even use try-catch blocks now with our asynchronous code, which is something you couldn't do before with just regular promises. So that's kind of a high-level overview. Let's kind of really dive in and understand async await a little more and figure out some use cases. So we'll start off by looking at this await operator to really understand what it's accomplishing. So I'm going to have some code like this where I have a fetch order. It takes in an order ID and it just uses the fetch API to make an HTTP request for the order. And then I'm going to use a print order function to call it. And notice I'm using the typical then callback here. After I fetch the order, I use then to basically, when it resolves, I get the order and I can do something with it. Well, imagine that then is essentially that await operation that we just saw earlier. So we can replace that, use await now, we'll await that promise we get back, and it's essentially like we had done that then callback to get the order, but now we get it in a synchronous looking fashion. And so it's going to give me back the order and I can assign that to a variable. So the way I kind of like to think about this await operation is, let's treat promises for a moment like a box. So fetch order doesn't return an order, it returns a promise. So it's like it returns a box that contains our order eventually. So what happens when we await this box? When you await it, I'm essentially waiting on an empty box. This is an empty promise, it's not fulfilled yet. So it's like this is a box that's empty and we're waiting for it to be filled up. Once it does get filled, await will notice that, and then it's going to do a couple things to basically get that order to us. First, it's like it's going to cut open the box so it can get to that value, and then just basically pull it out. So this is basically, in a way, just looking at pictorially, kind of underneath the hood, what await is really doing to get us these values out of these promises. So we see how that kind of works, but what happens after? So I've mentioned this is synchronous looking code, but it's still underneath the hood promises and it's asynchronous. So we're going to log out the order here. How is that going to happen in this case? Because if we tried this with just normal asynchronous code without an async function, this wouldn't work. It would go through the function immediately. We can't reference the order yet. Let's kind of look through an example invocation of this async function. And let's just imagine we're going to transpile it, like Babel might do. This will not be exactly what Babel code will look like, but it's semantically similar, so kind of a high-level view of it. So we invoke the order, we're going to encounter that await, and that's going to tip us off to do something here. Whatever we're awaiting, whether it's a promise or actually whether it's not, because we can await non-promises, we're going to wrap it in a call to promise.resolve. And again, we're just pretending like we're transpiling this into the equivalent promise code. So we'll translate it into something like this. So what I'm doing is I'm guaranteeing I have a promise at this point, because if I await a non-promise, I'm going to wrap it with promise.resolve to turn it into a promise. I'm just basically creating a consistent API here. And I can wrap other promises with promise.resolve, and it sort of just flattens itself out and gives me the fulfilled value eventually. So I have a promise now, I've transpiled it down to a promise. So then what I can do is for that next line to work, really it's as if that line needs to be contained within a then callback. So that promise I created up there, I can attach the then callback that will fulfill with the order, and then the rest of my code that gets transpiled down will just work, because underneath the hood, async await is basically doing this for us, and we don't have to write all of this promise code. But notice now in this pseudo transpiled code, we're saying we want to return promise.resolve of undefined. And the reason that happens is because when we return from an async function, if we don't return anything, we're implicitly returning undefined, like any other JavaScript function. But the transpiled code says we should wrap it with promise.resolve. So let's look at a simpler example. Let's say we have an async function called meaning of life, and it returns 42. Does that mean when I invoke this, I'm going to get back 42? If this is an async function, we can't depend upon a synchronous value coming back. So technically, async functions return promises. So notice the transpiled looking code will just wrap that 42 with a promise, and that's what we get back from async functions. And so whenever we're finally consuming these things, we got to remember, internally they still are promises. So at some point we might still need to use then callback. So that is one small limitation still. So switching gears now, let's look at how we deal with error handling with async await. I mentioned earlier that we could do try-catch blocks now. And what's nice here is that I can catch both synchronous errors like normal JavaScript code, and I can catch asynchronous errors now with this try-catch block. So if the HTTP request failed, I can catch that. And I can catch it down here like any other error. So what kind of errors then would this be catching? Let's say we go back to our fetch order function, and after we fetch it, we check the status code, and it's a 404, so the order wasn't found. So we'll throw an error. We're throwing an error in a then callback, and prior to async await, we couldn't just try catch that. We would have to do the catch callback. But with async await, we can catch that with the try catch block now. So we're able to reintroduce all these native flow control constructs in a synchronous looking manner. We can also catch rejected promises. So if I had an API that was using some legacy jQuery code and I want to wrap it in an ES6 promise, and I reject if the status code is 404, I can also catch that. But now, what does that tell us though? If we're still dealing with promises underneath the hood, and we're dealing with errors, we still haven't quite solved this issue. So if we neglect to use that try-catch block, we still run the risk of errors being swallowed. So we haven't quite solved this issue yet where if there's an error thrown, we'd like to know if we forget on our behalf to do a catch callback or do try-catch. So if we can do try-catch blocks though, can we use other sort of native flow control constructs? And yes, we can. So we can use things like if-else statements with async await. So I can, in my if check, I can await some operation that might fulfill to a Boolean. And then the same thing within those branches, I can await things in the if branch and the else branch. So it all just sort of works, but it's all asynchronous underneath the hood. So we can express more complex flows that would be a little more difficult with promises and do it in a synchronous manner thanks to async functions. We can also do this with for loops. I'm using the for-of loop, which is a newer feature in ES6, but it's a lot cleaner than doing a normal regular for loop where you're iterating on some I variable and incrementing it, basically. So notice here, inside the loop, I can await, which basically waits for that to finish, and then it does another turn of the loop. But could that create a problem, actually? And this is one of the gotchas we need to think about. If I'm basically looping over an array of order IDs, 1, 2, 3, and I want to fetch each order in turn, I'm basically blocking fetching every order because I'm kind of serializing this. So every time I await in the loop, I'm pausing. So essentially when I loop through here, I'm going to await the first order. I'm in the loop. But effectively, the second order and the third order, I can't even fetch them yet because I'm waiting inside the loop for this first one to complete. Once it completes, then I come around to the second order and I can fetch it. Similar thing with the third order. It's been waiting for the first two orders to even be fetched and finish. So if those response times are slow on each of those, that's going to be a cumulative effect. It's going to cause my code to be not as fast as it could be. So ideally, we don't have any dependencies amongst these orders. Why can't we just fetch them all at once? So order is very important here, and we can do this with async await. The trick is to use promise.all. So if you're not familiar with promise.all, it takes an array of promises, and it waits for each promise within that array to fulfill before this outer promise that we create with promise.all can fulfill. So if that returns a promise, why can't we just await it instead? So effectively, I can dispatch all the orders at once, all the fetches for the order, and then await promise.all. So it's sort of like, if you're familiar with this idea of barrier synchronization algorithms, it's effectively the same thing where we can just wait for all of them to complete, but they can run in parallel. So now they fetch all at once, and then the time that I'm limited by is only really limited by whichever of those orders is the slowest, because they can all run in parallel. I don't have to let their response times kind of be cumulative. So we get better performance out of doing that, and that's just kind of one of the gotchas that we have to watch out for with async await. So let's kind of review where we've been so far. We've quickly looked over async await. We've been able to kind of handle some of these things we had mentioned earlier. We can do readable, synchronous-looking code, but it's non-blocking and it's still asynchronous. And we can integrate these native flow control constructs. And we even saw one of the gotchas where we could have sequential processing that we didn't intend to do, and we flipped it over to concurrent processing instead. So now let's kind of switch gears and spend the rest of our time really diving into something different. So far, we've only been talking about like asynchronous HTTP stuff, but we haven't really considered the other side of asynchronous code, events and streams. And this isn't something we really typically use promises for, so it's not something we want to reach for async await. But we would like a better way to handle this with the newer asynchronous manner. So let's say we have some very simple code like this, where we have a counter variable set to 0, and we have an update counter function that helps us increment that counter and then update the DOM with it. And then we'll create a couple event listeners. And so this is a typical approach we might handle it with vanilla JavaScript, where we want to click an increment button or a decrement button. But imagine as our code base might grow, if we're doing a lot of jQuery, this can happen, where we get a lot of spaghetti code, where we have all these spread out event listeners, and they're all mutating and affecting state. So we're kind of lost as to where changes may be happening in our code base. So really, we don't want to take this callback approach to handling events and updating state. Well, this is where we can now reach for another newer asynchronous primitive, the observable. And we won't look in too much detail at this code yet, but just to give you an example, we can accomplish the same thing where we're basically streamlining changes and treating them as a stream of data with observables. So we're going to talk primarily today about RxJS Observables. It's a very popular library for doing reactive programming with observables. But observables are actually on track to become a standard feature of JavaScript. They're in the proposal stage right now. And RxJS's version of observables basically is trying to adhere to that standard spec, so that once the real standard comes out, you can almost basically swap out to the native if you want. So let's kind of look at what are observables and what are they useful for. Let's start off by thinking, okay, what is an observable? And I want to step back and let's think about arrays for a moment. We typically think of them as just a list of items that we can index into. But what if we treated them as sequences? Sequences of items, and they're sequences in space. So we just have all the items up front in memory. So if we think of them as sequences in space, we can look at observables and think of them as sequences in time. So they're like arrays, whereas instead of having all the values up front, we're going to get the values over time instead. Observables are also reactive, which what that really means is that as I get values out of my observable, I will react to them. I can transform them, do useful work on them, and then whatever value I get out, I can use later on. So we're just reacting to these items as they come through over time. So to create a very basic observable, we can use RxJS for that. And I'm using common JS style here where I'm requiring it and then using the ES60 structuring. But it's basically if I require RxJS, it exports an observable property that I'm pulling it out. And it's going to be essentially a class. So I require it here. And then I can create the most simple observable by calling Observable.of and pass in a variable number of arguments, 1, 2, and 3. So I'm creating an observable that only has 3 items in it. To get to those items, since this is basically like a stream of data, I can subscribe to the observable. And then every item that comes through will be passed to my anonymous callback I provide here, and I'm using arrow functions here. So every X I get, I can log out, 1, 2, and 3. So if we treat this as a timeline, it's essentially something like this, where items are coming through the timeline of my observable, and they hit my subscribe where I can log out the value one at a time. So that's a very basic idea of what's going on with observables, sequences in time versus sequences in space, like an array. But for them to be really useful, we want to start transforming and operating on them so we can do useful things with this data that's coming through on these observables. So let's talk about declarative transformation. So declarative transformation, it's decided declarative is just a way to describe how I want to operate on the data. So observables have tons of these operators. Probably the most well-known is called map. And map is just a way of transforming the data. So I provide to it a mapping function, and this is similar to array.map if you're familiar with using map functions on arrays, where I say for every item I get, an n, I want you to just turn that into n times 2. So if I have an observable of 1, 2, and 3, I effectively, as the values come down, I want to transform them into 2, 4, and 6. And then I'm going to end up logging out to the console those values instead of the original values. So the timeline on that is going to be something like this. So as I get a value, it's going to hit that map operator. So we have 1. I'm going to transform it into 2. That 2 then gets passed on to subscribe in console.log. Same thing with the next value, 2. We get that, we map it to 4, and that goes along to subscribe and print it out. And then finally 3 comes along where we map it to 6, and we print that out. So that's just a very basic idea of starting to transform data and do useful work on it. These transformations are also lazy, which means we only do as much work as we really want to, which is very different from using these operators on arrays like map. So we can do a lot of things on these values and do only as much work as we really want. So in this case, I'm going to use observable range. And really what I'm doing is I'm just mimicking the idea of having practically an infinite stream of data. When I use observable range, I'm just creating an observable of 1 to 100, so it's an inclusive range in this case. I'll again map every number, so then I'll have 2, 4, 6, etc. And now I'm going to use another operator that RxJS gives us, which is the filter operator. And the filter operator takes a function, callback, and it allows us to specify which values we want to keep. So I'm going to say take in and only keep it if it's greater than 4. So I'm only interested in values that are greater than 4. And then I'm going to use another operator called take here, which allows me to limit how many values I ultimately want to get out of this observable. But the idea is, as opposed to an array where if we call map and filter on array, we iterate through the array 2 times. We iterate over it to map it, and we iterate over again to filter it. That's not the case here. With an observable, we're going to apply all these operators to every value. So we're essentially iterating only once, even though it's a stream of data. So with the timeline then, when I get 1 here, it hits map first. I want to double it. And like I said, instead of waiting to iterate through the other values and map them, we're just going to pass it along to filter. It's not greater than 4, so we're going to drop it, and then it won't even go on down the pipeline. There's no reason for it to hit anything else, because we're not interested in that value. If I do 2, Comes through, we map it to 4. Again, it comes to filter. 4 is not greater than 4, so we drop it. Now we get 3. It comes into map, so we map that to 6. That hits filter. It is greater than 4, so we allow it to keep going down the timeline, and it hits that take. We only want to take 2 values, so we'll allow it to pass through to subscribe, or we can print it out. And now we decrement how many values we want to take. So now we're only interested in taking 1 value. Finally, 4 comes through. We map that to 8. We hit the filter. That is greater than 4. It goes along to take. And then we're done. And notice, even though we had 100 values, or we're mimicking an infinite stream of data, we only had to go through 4 values before we were complete. And so that's a lot more performant than doing work with arrays where we have to loop through tons or iterate multiple times with a map and with a filter, etc. So now let's start applying some of these ideas, and let's revisit how to do some more useful work, like interacting with the DOM and doing DOM events. So we had looked at that earlier example where we can increment or decrement a counter by clicking a button. So let's use observables to accomplish that, and we'll start off by just incrementing. So we can listen to events and create a stream of data from events by using observable from event. We provide to it the DOM element and the event name that we're interested in listening to. But we're not interested in the event object that the DOM is going to generate for us. We're just interested in the fact that this event occurred. So we want to transform this into some more useful data that we can use to increment a counter. So we'll use the map_to operator. It's just like the map operator we saw earlier, but we don't take in a mapping function. Instead, we just provided a static value. So what I'm essentially saying is every time you click on this button, which means there was an event object, I want you to just transform that into the number 1. So I'm effectively creating a stream of just the number 1 every time we click. I'm going to use then a scan operator, and we'll look at it more thoroughly in depth in a moment. But essentially it's going to allow us to accumulate a value, which is the counter value. And then when I subscribe here, the value I'm getting out at this point, I now have a stream of the value for the current counter, and that's what I can use to update my DOM here. So you can imagine you could swap this out with a view layer too, like React or Angular or something like that even. It doesn't have to be just vanilla JavaScript here. So looking more closely at that scan operation again, it takes 2 arguments. It takes a callback and an initial value. This callback takes 2 parameters. The first argument is our accumulated value, which in this case we want to be the counter value, which starts off at 0. That next argument is the current value that is preceding this in the timeline of the observable. And remember, that is the number 1 because we're mapping events to the number 1. When we hit the scan, what we want to return is whatever we want the new accumulated value to be. So we're going to have accumulation plus the current value. So that would be, when we start off, 0 plus 1. And then we would have 1 plus 1, 2 plus 1, etc. And then the second argument is just whatever we want the initial counter value to be. In this case, we want it to be 0 because we're starting off at that number. So the timeline then, when we have a click, remember we have an event object, but we're not interested in it. We're just interested in the fact that it occurred. So we're going to go ahead and just transform that with map_to to a 1. So now the observable is observable once. It comes to scan, and then we're going to increment that with the counter value. So we had 0 plus 1, and now the observable is whatever the current counter value is. And that's what gets passed along to subscribe. When we have another click, we'll map that to 1. It'll come into scan, and now we're going to have 1 plus 1 to give us a counter value of 2, which we can pass along to subscribe. So we understand how to do the increment now. We've kind of done all this with just a few operators with an observable. We can now start to go back to that increment-decrement approach. So we're going to use observable merge here. And as it suggests, it's going to merge together 2 different observables, or as many as we pass into it, but basically creating one observable out of many. I'm going to provide to it two observables. The first one is what we saw earlier, where we create an observable from increment button clicks that we map to 1. But below that, notice we're going to do the same thing with the decrement button, but we're mapping it to -1. And when we merge these together, we effectively have an observable of 1s and -1s. That's all it is. And then we introduce our scan operation just like we saw before, but now the current value is either 1 or -1. So the timeline then is we merge these together and we create one observable. So when we click increment, we map that to 1 just as before. It comes into scan and we do 1 plus 0. We've now got a new accumulated counter value of 1 that gets passed along to subscribe. Next, if we click the decrement button, that event object gets mapped to -1. That gets passed along to scan. So we have 1 plus -1, or 1 minus 1, which causes it to effectively decrement and give us back 0. And then that gets passed along to subscribe. So what we've been able to accomplish, though, is we've kind of streamlined the changes that are allowed to happen to this state. Instead of allowing multiple event handlers to just be attached wherever they want and affect this state on their own, we've basically said, here's where changes can happen, and I'm locking it down to this observable of 1s and -1s in this case. So moving along now, away from the DOM, let's kind of revisit asynchronous HTTP and look at how we can actually use observables for dealing with HTTP as well. So to understand how we might be able to accomplish that, we could have some promise code like this we saw before. We fetch the orders, we attach it, then callback, till we eventually get this array of orders back. Well, we can actually translate this really well to observables. Instead of having then there, why don't we have subscribe there? So we can imagine that fetch orders is just an observable that makes the HTTP request for the orders, instead of using a promise here. And one little benefit we get out of that is that it turns out until we subscribe to an observable, it actually doesn't do anything. It's just a value. So it's lazy. So whereas when we call fetch orders that returns a promise, it immediately makes the HTTP request. When I use an observable, it does not do that until I choose to subscribe to it. But why would we use observables in this case? Observables are great for events, they're great for streams of data, but why would we use it for just a one-off value that we could use a promise for easily? Well, there's a few reasons that we're going to go through, and we'll see that it might be beneficial to use observables. So one thing is, going back to that declarative API issue, so if I use a promise here to fetch this array of orders, and let's say I want to filter them, and I want to map over them to their ID, and then I want to print out all these order IDs. Well, to do that with a promise, I have to attach a ton of these then callbacks, and I'm essentially hiding away inside of that then callback the filter process, where I filter the array, and I pull out orders that have a customer name set to Tucker. Same thing here when I want to map over them. I have to attach a then callback, grab the orders and map over the orders. And then when I want to loop over them and print the ID. The basic idea here is this idea of me filtering, mapping, and doing all this process, it's getting hidden behind all these then callbacks. So it's not as nice and expressive as we might like. So we could fix that with async await that we learned about earlier and write it in an imperative style. So I can await the fetch orders, get the orders out, and then have it look a little cleaner by having it in this synchronous looking manner where I can filter and map and etc. But let's try the observable approach and see what we can do. Let's say fetch orders returns an observable now, and it's an observable of an array. But I can use a merge all operator, which is a very versatile operator that we'll revisit in a moment. But it essentially can flatten out that array of orders within my observable and basically feed me every item one at a time, to where now I can use the native operators on the observable, like filter, so I can filter every order, I can map every order, and then subscribe and print each one of them out. So I've been able to reduce the amount of code I wrote here and more cleanly express what I wanted to accomplish here with the Observable API. Another benefit of observables over promises is cancellation. So let's say I have promise code like this now. We're using a promise again. I'm fetching the orders, and let's say I suddenly want to cancel that HTTP request. I could try something like this, but with native promises, that doesn't exist. We can't cancel an in-flight request unless we use a third-party library that does their own promise implementation. But we can do this with observables, whether it's RxJS or the standard spec that's going to be hopefully added to JavaScript in the future. So I can call unsubscribe. Whenever I subscribe to an observable, I get back a subscription. And it has an unsubscribe method. And that unsubscribe effectively allows me not to only stop listening to events, but it can cancel any in-flight requests. So that's another benefit we can get out of observables over using a promise-based API. So if we want to use these observables for HTTP, how can we actually create these HTTP requests? Well, one approach is very simple. RxJS does give us some helpers for that. So it can be as simple as doing something like this. It has an AJAX object on the observable, which has methods for the different HTTP methods. So the GET method would obviously perform a typical HTTP GET for those orders. But let's say maybe we're working with some legacy APIs and we have to do some manual observable creation in order to do this type of HTTP request. So another way we can do it is create a custom observable where we can do Observable.create, and we provided a callback. That callback we give it is going to provide us with what we call a subscriber. And the subscriber is basically the listener that wants to listen to the events or the data that's coming down the pipeline. So I have this legacy API where I fetch the orders from the database, and it requires a callback that takes the orders. Well, then I can use that subscriber that the observable has provided to me, and I can call its next method, and I can provide to it this value. So I can sort of feed in data from different sources, like this legacy API. And then I can use subscriber.complete to basically say there's no more data, we're done, and so you have all that you need. But where does this subscriber really come from? What is a subscriber? So we have a lot of words floating around: observable, subscription, subscriber, and whatnot. Well, if we look back at this simple example, observable 1, 2, and 3, that callback we provided to subscribe was our subscriber. It was just sugar for that next function that we saw earlier. So in fact, it's no different than if we had passed in an object. So we can pass in objects to subscribe as well and specify what we're interested in listening to. So I can specify next and give it that callback, so it'll give me every next item and allow me to do something with it, which in this case was printed out. And we saw that next callback earlier when we were invoking it in our custom observable. That means we can also provide a complete callback here as well, which effectively is a way that if this observable is done giving us data, we can be notified of that with this complete callback. Now, there's another thing we can do with subscribers that allows us to start looking at error handling a little more. So we have next, we have complete. We can also listen for errors. So I'm creating a simple observable up here, and I'm calling subscriber.next, passing in 1 and 2. So it's a stream of data of 1 and 2, but in the middle, I can call this subscriber error method, which is effectively like throwing an error on the subscriber. So I can catch that here, and we could catch if there was a thrown error in an observable as well, similarly. But notice there's a problem here. When I catch that error here, I've only gotten the 1, and then I caught that error, but I'm not going to get any more stream of data. This error callback is essentially saying I've recovered from the error, but I'm done dealing with this observable. We might want to retry something or recover and keep the observable running. So let's revisit error handling, learn how we can do that, and see another benefit that we get out of observables that promises can't offer to us. Recall again, promises, they swallow errors. That's a big issue because if we're not notified of errors, we can have bugs in our program or get into inconsistent state. But if we look at observables, what we just saw with this subscriber error method, what happens if I don't provide an error method there, but there's going to be a thrown error or subscriber.error called on that observable? It's actually going to blow up and it's going to throw an error and it's going to tell me. So observables won't swallow errors. They will let us know if there was a problem. And that means we can be notified a lot sooner if there was an issue in our code and fix it versus not being known when the promises swallow errors. So how can we recover from this too? There's actually a catch callback, just like promises on observables. We can catch the error, do something with it, like log it out to let us know, and then we have a chance to recover and keep our observable running. In this case, I'm doing something simple, and I'm just going to return an observable of an empty array, and just basically say I want to treat this fetch orders call that failed, and just use an empty array as the value I get out of it. But you could imagine you could try to retry the call or do other backup plans, so to speak, to recover here and keep your stream of data going. So one thing I want to revisit now is looking at something we're going to eventually see called higher order observables, and I want to revisit this merge all. We talked about earlier when we fetched an array of orders, we could flatten that array out and process each item at a time with the observable API. So if we had an example like this, notice here we're doing observable of an array of 1, 2, 3. When I subscribe to that, it's going to give me the array, not every item yet. If I introduce that merge all operator here, though, it effectively flattens that array and then gives me every item at a time again. So the timeline for that is you have the array, it encounters merge all, and it's going to pause. Observable is going to see that it's an array, and it's going to slowly pull values out and send those down to my subscribe instead of sending the array down. And so that's effectively what merge all is doing. But merge all actually works on other things besides arrays. And that leads us into our final topic, which is looking at higher order observables. Now this is a really fancy term, but it's basically when you have an observable and the values inside it are also observables. And we're going to see how that's a useful feature for doing something later, but we'll see, like rate limiting. So let's say we have our observable 1, 2, 3. We're mapping it to double every number. And let's say instead of printing every item out one after the other really quickly, we want to delay that. So we want to introduce like a 1-second delay between each time we print out a number. We're going to need two things to do that. So let's take it one step at a time. Let's first talk about this observable of observables idea. So instead of mapping n to n times 2, I want to map to observable of n times 2. And when that gets printed out in the subscribe callback, I have observables coming through instead of values themselves. I can reintroduce merge all, and merge all can not only flatten arrays, it can flatten the observable, which is a way of saying, take the value inside that inner observable and use it in my outer observable now. So I can get back 2, 4, and 6 here. So that's the first piece. In fact, we can condense that operation down into something called merge map, which does the merge all and the map in one operation. So I merge map to the observable of n times 2. So what that's effectively doing is, when I get 1 here, merge map is going to create or map that to an inner observable above, which is observable of 2. That outer observable on the bottom is going to subscribe to the inner observable that it just created. That inner observable is going to produce 2, and we're going to pull that 2 back down into the outer observable. So this is the first piece we need. We need a higher order observable, which is just an observable of an observable. The next piece we need is how to delay something, because we want to introduce that delay. So I can create an observable with just one value here, observable of 1. And I can use this delay operator to delay it by a second, so that when I subscribe and print, it's going to wait a second before we print out 1. So that's the second piece. So if we can have an observable of observables, and we can delay observables, then we can have an observable of a delayed observable. So here I'm doing the observable of n times 2 with the merge map, but I'm also delaying it by passing in 1,000 milliseconds. So it's effectively delaying it by a second. But we're going to interestingly run into a gotcha here. It's going to tick once, but then everything's going to get printed out at once, and that's not what we wanted. We wanted to wait a second after every one, so introduce a second delay between each of them. So what we're running into is a concurrency issue here, and that's an important gotcha to consider. RxJS wants to, by default, treat things concurrently to give you better performance, but that's not something we wanted here. So what we just did was, as items came through, we mapped them. So we mapped that to observable of 2, and that's waiting the second before it gets printed. But then we're allowing the other values to come through, and effectively these all can run concurrently. And it's not until they all complete at once, because they don't know about each other, so they effectively are all in the event loop, and they all resolve within a very short time frame of one another, and then we just print them all out at once. So we can fix that a couple ways. One way is we can introduce this second argument, which is the level of concurrency. So I can say I only want one item running at once, so my concurrency level is 1. So now I can introduce that 1 second delay between each item. So they have a tick and 2, we wait a second and we do 4, and we wait a second and do 6. Now an easier way to do that is we can also either use that, or we can use a concat map, which is effectively merge map with concurrency set to 1. But as you can see, the name suggests it's mapping and concatenating instead of allowing these things to run concurrently. So as values come through now, we concat map, but we're only allowing one observable at once. So we have to wait for it to complete before we can grab the other values. And so they all have to go through one at a time. And so that solves that issue, and now leads us into what the ultimate reason why we'd want something like that would be with rate limiting. So if we're encountering rate limiting APIs that maybe throw an error whenever we hit an error limit, instead of receiving those errors, why don't we rate limit ourselves up ahead? So if we can delay just some normal number printing, why can't we delay an AJAX request too? So we can use concat map. We can take those order IDs, 1, 2, 3, map those to an AJAX request for the order, and delay it. We'll use a couple other helpers here, because I'm using their API from RxJS. And I can use this pluck operator, which is like map, and it takes a property of the response out for me. So it just kind of plucks it out. And then I'll use buffer count to effectively take each of these orders I'm getting, because it's running one at a time. I'll buffer them back up into an array for me, because I expect 3 items here. So what we get is we map ID 1 to an AJAX request. That's going to be delayed though, so even when I get the response back, effectively we're rate limiting the next request. So we're limiting ourselves up front so we don't hit the rate limit on the API itself. Once we get the response, it comes back down to our outer observable. We can pluck it out, get the order, and then hit the buffer count to throw it into a buffer where we're just essentially buffering it up into an array. The other ones come through, we buffer those up, and now we've hit the buffer limit, we're at 0, so we know we can get back the original array. And so that's kind of a brief overview of just all of the things we can accomplish with observables. There's a lot more that you can do, with, such as concurrent processing, like we saw earlier with async await, and lots of debouncing and throttling and other things. But we've been able to solve some of the issues we talked about earlier. We now have a more declarative API over promises, and it gives us lazy operations. We saw we can do expressive event management with the DOM events and the counter, incrementing and decrementing. We also learned that we don't have any more error swallowing to worry about. And then we saw the rate limiting and saw how there is concurrency as well, concurrent processing in observables. So finally, just some resources, and these slides are available online too, so if you don't want to worry about quickly snapping shots or anything, that's completely fine. But just to let you know, there are some URLs where you can check what is currently the compatibility for async await, what browsers you can use them in, what versions of Node you can even use them in. Additionally, we can use Babel to transpile all this for older browsers. As far as observables, we've talked about RxJS and how we can use that. And then there's also a URL if you're interested in following the current proposal for adding observables as a native standard to JavaScript, as well as another implementation. And that's it. Thank you all so much. I appreciate you joining me today.